Imagine yourself on a bike. Would you rather go down this hill or this one? Well, if you're somewhat sane, you'd probably like to go down this one. But why? In this chapter, we're going to learn about slope, or the steepness of a line on a coordinate plane. The target for this chapter is I can determine the slope of a line and recognize constant and variable rates of change. Some of the key vocabulary you'll see is a slope. Slope measures how steep a line is using the ratio of rise to run. And a slope can be positive or negative, but ultimately shows us a rate of change. And this rate can be constant or variable, and it can help us solve real-world problems. So as I mentioned earlier, the slope of a line is a measure of how steep it is compared to its rise and its run. So let's take a look at this red line. If we spin it, right now we've got a really steep angle. Imagine going down it on a mountain bike or a sled. That'd be really steep. But if we move the line closer to be parallel with the x-axis, it gets less and less steep, meaning the slope decreases. So we've got a small slope and a much larger slope. So we can classify a slope in a couple different ways. First, we can classify it as positive, or we classify it as negative, 0 or undefined. But in this case, we're mostly going to be looking at positive and negative. So the slope is positive. As we read our graph from left to right, just like we read a book, our line will rise, kind of like you're hiking uphill. If our line is negative, then it will decrease as we move from left to right, like you're going downhill. This is the first you try. Don't worry, there's plenty more to come. But in this one, tell whether the slope is positive or negative. Go ahead and click pause, and then we'll go over the answers. In problem number A, as we read from left to right, we see that our slope decreases, or it slopes down. That would mean that we have a negative slope. In option B, as we read from left to right, our slope rises up, which means that our slope is positive. So if a slope is a measure of how steep something is, we can actually give it a number by looking at the ratio of how much it rises over how much it runs. And we can see that in the equation below. Another way to look at it is the vertical change over the horizontal change, or the change in y over the change in x. We'll get into this part later. But let's take a look at rise over run. So in our graph below, we have a line, and it has a slope. If we want to know what that slope is, we pick a point, and it's best to pick a whole number point. So a point that has whole numbers. Then we go ahead and pick another point on our line, a point that is at the intersection of our grid lines on our coordinate plane, or in other words, a whole number. So our next point is going to be over here. Now that we have our 2 points, all we need to do is figure out how much we rose, or how much we moved vertically, and how much we moved horizontally, or our run. So in this case, I'm going to choose my starting point as the blue point down here. And how far vertically did I move to get the same y value as the red dot? Well, my rise was 1. Now how far did I move horizontally? In other words, what's my run? How far did we move horizontally to get to our next point? So in this case, it's 1, 2, 3. So our slope then is 1/3, 1 over 3, where 1 was our rise and 3 was our run. You try. For these 2 graphs, find the slopes. Go ahead and click pause now, and we'll go over the answers. So if you remember, our slope is our rise over our run. So the first thing that we want to do is we want to find our starting point. I'm going to choose, for our first graph, the point 2, 2 as my starting point. So the first thing I'm going to do is I need to figure out my rise, or what my change in y value is. Remember, my y value is the up and down, the vertical. Okay, so I start off and count in whole number increments. 1, 2, 3, 4. So I rose 4. Now, how far did I go over? 1, 2, 3, 4. So I went over 4. If we simplify, or divide by the least, or the greatest common multiple, that would turn to 1, that would turn to 1. And so our slope now is 1 to 1. So for every 1 box I rise, I move over 1 box. For every 1 box I rise, I move over 1 box. And that gives us our staircase of 1 to 1. So let's go on to problem 2. So we're going to write our formula again. Rise over our run. And we'll find a starting point. So I'm going to choose this point as my starting point. Maybe you choose differently, but that's okay. You should get the same answer. So if I start at -4, 5, I need to find out my rise, or what my change in y, what my change in my vertical axis was. So because I'm counting down, and as you go down the y-axis, it gets negative, we're going to count in negative numbers because we're counting down. We're falling. So -1, -2. So I have, let me use a different color. So I have -2 as my rise because I went down. And now I need to figure out my run. Now, in this case, our run is actually moving in the positive x direction. As we move to the right, x gets positive. On the left side of our coordinate plane, x is negative. So we are actually counting in positive numbers because we're moving to the right. So 1, 2, 3, 4. So our run is a positive 4. Again, we can simplify this fraction by dividing by the least common multiple. So looks like they're both divisible by 2. So if we divide 2 by 2, or sorry, -2 by 2, we get a -1. And if we divide 4 by 2, we get 2. So our slope then becomes -1 over 2. And hopefully this kind of looks familiar, because if you think back to the first part of this video, you looked at positive and negative slopes. This slope here that we just found is negative. Does our line look negative? Well, yeah. As we read from left to right, our slope slopes down. Previously, we found the slope of a line given 2 points. In this example, we're actually given a point and then a slope. And from those 2 bits of information, we can graph a line. In example A, our point is -3, 2. And that is where we're going to start, because we need a starting point to do our rise and our run. So our starting point on our graph is -3, so 1, 2, 3, then up 2. And there is my starting point. So now that I have my starting point, I can look at my slope, or my rise over my run. So I have -3/4. So first, I'm going to do my rise, which is, well, -3, which means I'm going to move in the y direction, -3. So 1, 2, 3. Okay. And now I go +4. And since this is my run, I'm going to move to the right, +4. 1, 2, 3, 4. Then I have my new point. And if we connect the dots, voila, we have our line. It's also important to note that our slope, -3/4, or -3/4, can also be written as 3 over -4. The negative sign can be in the numerator or the denominator, just not both. So let's try it. Let's try graphing, starting at our starting point, using a slope of 3 over -4. So first we have a rise of 3, 1, 2, 3, and then we have a run of -4. As you can see, this gives us another point on our line, or another point for us to draw the line using our starting point. So no matter what slope you use, -3/4 or 3 over -4, you'll get the same line. Now it's your turn again. We're almost there. We still have one more topic to cover. But in your notes, draw a coordinate plane and graph the line using a slope and point for each of the 2 points. Go ahead and click pause now, give it a whirl, and continue playing for the answers. So for our first one, let's take a look. The first thing we need to do is plot our point, or get our starting point for our line. So that is 4, -2. So I'm going to go over 4, down -2, and my point goes right there. Next, I'm going to use my slope. Now my slope is 3, but I can also write 3 as 3 over 1, like any whole number. So from my starting point, I'm going to rise 3, which gets me there, and then I'm going to run 1, I'm sorry, to get my new point. And if I connect the dots, I have my line. So in the second example, same thing. We start with our starting point, -3, -2. So I go back -3, and then I go down -2. All right, and same thing as before. My slope, we can put over 1, if it's not already a fraction. And that's telling us we need to go, our rise is -2, so we need to go down -2. 1, 2, and then over 1. I use the dots as a guide, and there's my line. Another way of saying slope is calling it a rate of change. It is the rate of change of the 2 quantities on an x and y axis. Now a line with a constant rate of change is a line where the slope will never change. So if we look at graph A, our line has the same slope from here to here, from here to here, all the way. And their slope will continue on the same path. The line will continue on the same path forever and ever, which means that our slope is never going to change. On the flip side, if we look at a graph that has a variable rate change, it's going to be a graph where the slope changes over time. So if we look at graph B, our slope right here looks like our line is traveling in that direction. But up here, the line is now traveling in that direction. And over here, well, the line slope's actually negative over here. In essence, a variable rate of change will never be a straight line because the slope will always be changing. So let's take a look at an example. We have a graph of a bicyclist traveling a certain distance, or the y-axis, over time on the x-axis. Does a bicyclist travel at a constant or variable speed? So, constant meaning, does our line change slopes over time? That would be variable. Or does our line have a constant slope the whole time, forever and ever? Well, if we take a look at our line, it's like it continues on the same slope of 15 over 1, forever and ever. So, our slope does not change. It is constant. Now, if we want to know what our slope actually is, well, we just put our rise over our run. So our rise is our distance, and our run is our time. So what we're looking for is distance over time. Our slope is telling us that our bicyclist goes 15 miles every 1 hour, or 15 miles per hour. So I swear this is the last one. Go ahead, give it a try. Find out if the line is showing constant or variable speed, or if the slope is changing or not over time. And then figure out how fast does the trout swim. Go ahead and click pause now, and we'll go over the answer. So the first thing that we're going to do is we're going to find whether we have a constant or a variable speed, or slope. So we want to see if our slope changes over time or if it remains the same. Because it is a straight line, our slope will never change. It will go on forever and ever in the same path of travel. The other thing it's asking is how fast does the trout swim? Or what is our slope of the line? To do this, you guessed it, we put 2 points on our graph. We want to make sure they're whole numbers. So I know that my line is crossing this point right here of 4,60. And I'm not sure if it crosses there. It may look like it crosses here too, but I know for a fact it starts right here at 0,0. So my change in y over my change in x. So my rise over my run. So if I use this as my starting point, how far did I go up to get to 4,60? 20, 40, 60. And how far did I go over to get there? 1, 2, 3, 4. So 4 was my rise, and 60 was my rise, and 4 was my run. So I can write it over here. So my rise was 60 what? 60 miles. And my run was 4 hours. 4 hours. So that's my slope, but it can be simplified. 4 goes into 60 15 times, or 15 miles. And 4 goes into 4 just once. 1 hour. So you can see our slope is really just finding a unit rate. Our denominator is 1. So our trout swims 15 miles an hour. That's a fast fish. Whew. So thanks for watching. I know it was a long one, but we had a lot of important concepts here.